Very good morning, friends. In the previous class, we have discussed regarding power density and variation of wind pressure and velocity across the rotor. In continuation of that, we are going to discuss the power coefficient and other terms in this class. Here, the power coefficient is nothing but it is the ratio of power of wind rotor to that of power available in the wind, or the fraction of free flow wind power that can be extracted by the rotor is called as power coefficient. Here the power available is calculated from the air density, rotor diameter, free wind speed as discussed earlier. The maximum theoretical power coefficient is equal to 16 divided by 27 or 0.593. This value cannot be exceeded by the rotor in the free flow wind stream. So that is 59% is only the maximum power available theoretically. So beyond that we cannot achieve the efficiency of the wind turbine. Next definition is coefficient of performance. So here an ideal rotor with a propeller type of blades. Propeller type of blades means the blades which resembles propeller of a ship is called as propeller type of a blade of proper aerodynamic design. Aerodynamic design means the blades are made up of aerofoil shape. You might have observed in the highways the wind turbine blades are carried to the sides of installation. So the cross section of the blades will be generally having aerofoil shape. So aerofoil shape means like this. I am writing on the screen. So this is called as aerofoil shape. Okay. So whereas this edge is called as leading edge, whereas the sharp edge at the bottom behind is called as trailing edge. Now this type of blades of proper aerodynamic design would have a power coefficient approaching 0.59. Means if you use this type of blades which have the cross section of aerofoil shape, then you will achieve the maximum coefficient 0.59. But such rotor would not be strong enough to withstand the stresses uh, to which it is subjected when rotating at high rate in a high speed wind stream. So these blades will not withstand the stresses. Centrifugal stresses are induced because these blades are made up of some composite materials. Sometimes they are made up of some alloys also. Because of rotation, always there will be a centrifugal stress induced in the blades, and these blades sometimes do not withstand that stress and there are chances of breakdown. Therefore, so always it is not possible to use the aerofoil shaped blades. If we properly use proper materials to construct this aerofoil shaped blades, then power coefficient up to 0.59 we can achieve. Most often the windmill performance is also expressed in terms of coefficient of performance. So what is coefficient of performance? Here the coefficient of performance is nothing but it is the ratio of power delivered by the rotor to that of maximum power available in the wind. So compared to that earlier one, it is also similar to the earlier definition. Coefficient of performance is nothing but power delivered by the rotor to that of maximum power available in the wind. Power delivered by the rotor is nothing but it is after conversion what we get energy. The converted energy in the form of mechanical as well as electrical energy is numerator. The power maximum power available in the wind is the input to the rotor. Rotor diameter, wind speed and air density are used to calculate the actual maximum power available in the wind. So we have already know what is the equation used to calculate the P. So that depends upon the wind speed V, air density rho, okay, and rotor diameter D. So this is rotor diameter D, wind speed V, and as well as the air density rho. Okay, so these are the things on which generally the power delivered by the rotor depends, but under certain special circumstances the power coefficient cannot be greater than 0.593. Again it is same, power coefficient cannot be greater than 0.593 whatever may be the conditions or whatever may be the material, whatever may be the sophisticated technology you are going to use. Okay, the next derivation is instantaneous wind power. You can see V is the velocity. In actuality it is not constant. So you see that in the atmosphere wind blows at different speeds at a different time intervals. Okay, sometimes there will not be any wind. Okay, therefore it is represented by a statically noisy wind speed time curve Vt, then instantaneous power in the wind. So since it is not constant, we are going to express the instantaneous power expression. So that expression is similar to that of earlier power expression, but it is Pw suffix T is equal to half rho A Vt to the power of cube watts. So this is derived or taken from the equation 4.2, that is power equation. So here normally the average power is taken. Okay, and time average for both the sides are considered, and after considering the time average and average power, because power delivered will not be constant always in the wind turbine, it varies because wind speed also every second varies. Therefore it is a common practice to write the average power. So that average power is indicated by the a dash symbol on the P term as well as a dash symbol on the V term, that represents the average power for that given average velocity. Now the above equation results in a average wind power density, and it can be given by the following equation. In the earlier equation, if that power term is divided by area of the rotor, okay, on LHS as well as on the RHS. So in the LHS term you see that P dash WT divided by A will be equal to half rho V cube to the Vt to the power of cube, average cube. So A term on the RHS is absent, whereas in the denominator of left hand side you will get A term. So this P by A is nothing but we have already studied, this is power density. P is called as power, P by A is called as power density. So this equation 4.7 says that average available wind power per unit area is directly related to the average of the wind speed cubed. Okay, so the power density is directly proportional to the cube of the wind speed, that is V cube. So this is one useful method of characterizing the potential specific power in the wind over geographical area. So in this way we can, by this equation we can calculate or we can estimate what is the potential for a particular geographic area of converting the wind energy to the electrical power. So in practice the wind turbines output will vary. So this the output of the wind turbine always varies. There will be periods when there is a insufficient wind for a machine to generate any power at all, and at times when the wind speeds are so high that machine has a shutdown to prevent the damage. So there are always variations. Sometimes there will be no wind, so no power generation during that time. You might have observed during no wind condition the windmills have stopped turning or running. So in that case there is no power generated in the windmill, and sometimes the wind speeds are so high that wind turbines cannot withstand or cannot operate at that speed. So in that condition also, to prevent the breakages or damages, so the program is made in the controller in such a way that automatically the wind turbines will shut down themselves, so that there will not be any damage to the wind turbine. So next derivation is a maximum power. So we have derived the power density, average power density equation in the previous section. Now we have to go for the maximum power derivation. So it is clear from the above discussion that wind cannot be converted to mechanical power directly. Okay, so wind energy. So let us consider a small thickness AB of the wheel of the horizontal axis propeller windmill. Now this is one experiment they are doing. They are considering a thickness of the wheel, that is horizontal axis propeller windmill thickness they are considering. So in that Pi is wind pressure at the upstream side and Vi is the wind pressure at the upstream side, and Pe and Ve are the corresponding wind pressure and velocity on the downstream side. Means for this thickness AB on the upstream side, so upstream side means at the beginning of the thickness, and on the downstream side means after passing through the thickness. So the pressure and velocity terms are given here. So now, so we have to consider one more section IA as the thermodynamic system. So neglecting the change in the air density. So generally air density will change after passing through the rotor, but that change in the air density is neglected, and rho, that is air density, is kept as constant for this assumption or derivation. And potential energy between IA and no heat and work transfer. So during generally what happens, there will be a work transfer and heat transfer will happen because of the friction. So all these heat transfer, work transfer and potential energy existing between IA are all considered as constant or negligible. So in that case the general equation can be written as follows. So this is what they have written. It is called as Bernoulli's equation, where the fluid mechanics subject of fourth semester students, they are going to study this one. In the Bernoulli's equation we have three terms. One is called as pressure head, another one is called as kinetic head, and the third one is called as potential head. So now whatever the thickness AB or the section IA you have considered, it will have only the pressure head and a velocity head. There is no potential head because the thickness AB at the inlet section and the exit section both will be at the same height from the ground. Therefore be potential energy at the inlet and as well as the potential energy at the outlet will be zero. Now Pi into V is nothing but pressure head, V square by 2 is nothing but kinetic head. So this total energy, it is called as total head, means total energy inside the air at the inlet of thickness AB. Similarly this is the total energy at the exit of the is thickness AB. So as per the law of conservation of energy, energy neither be created nor be destroyed, only can be converted from one form to another form. Therefore considering the total energy at the inlet is equal to the total energy at the outlet, we are going to derive the maximum power. So how to derive the maximum power? Now divide entire equation by specific volume V. Now you see that on the LHS Pi into V was there in the earlier equation. After dividing that specific volume V term in the Pi, first term of LHS will vanish and 1 over V will be equal to density. In the second term 1 over specific volume will be equal to the density. You know that specific volume is nothing but meter cube per kg. So that when you send it to the numerator, this will be equal to kg per meter cube. Kg per meter cube will be nothing but it is called as density. Therefore here density is multiplied for the second term, whereas the small v term in the first term is absent. The same thing happens on the second term also. Pa into v term in the RHS of the first term will vanish, whereas 1 over v to the Va square by 2 is multiplied for the second term of RHS. That gives 1 over V is equal to rho. So therefore rho into Va square by 2 is taken as a second term. Now similarly for the section it will be considered. So this is for the whole I into A section it is considered, and for B into E again the same type of a expression we have written, where the initial section will be B and the exit section will be E. So there will be initial section, this is the point I, okay, this is A and this is A and this is B and this is E. So first equation is considered by between I and A. The second equation is considered between B and E. So from I to A and B to E it is considered. Now the same variations of pressure and velocity they have given in the following figure. You see that the pressure from I to A increases because this is the A to B is the portion where the wheel is there. So before the wheel the pressure increases, and while passing across the wheel from A to B in this region the pressure drastically reduces or drops. That pressure is converted into velocity, and from again B to E gradually it gains, and this is the atmospheric pressure, that is Pi and Pe are equal to the atmospheric pressure. Atmospheric pressure is attained after some length from the rotor. Similarly velocity, you can see it was earlier huge velocity was there before the rotor. Across the rotor the velocity drops, and also after the rotor it will not gain the original speed, but it will be somewhat lesser than the average speed or total speed Vt. Okay, so this velocity loss in the reduced velocity value after the turbine will be converted into mechanical energy or gain. Now this in the figure you see that the velocity in the wind between section AB decreases, that we have discussed. The velocity VA and the velocity VB, so are the velocities you just observe, they are the velocities at the beginning of the rotor and at the end of the rotor. So here the pressure, ambient pressure is greater than inlet pressure, and the pressure B, exit pressure at the section B will be less than the pressure A. So from this equations of 4.5 and 4.6 again we can write the following equations, that is Pa minus Pb is equal to Pi plus rho into Vi square minus Va square by 2 minus Pi plus rho into Ve square minus Vb square by 2. So this is again total head. Pressure is equal to total head. So equating these two, so we will finally simplify and get that Pa minus Pb. We want to get the difference in the pressure. Pa minus Pb is equal to rho into Vi square minus Ve square by 2. But the axial force is nothing but pressure into area. Pressure is Newton per meter square, area is meter square. Newton per meter square into meter square, meter square, meter square get cancels. The final unit will be Newton. Therefore we will get the fundamental equation of force is equal to pressure into area. Applying that we will get the expression for the axial force. Fx is equal to rho into A into Vi square minus Ve square divided by 2. So this is the expression for the axial force. Now in this axial force where A is the area perpendicular to the stream, and Fx is what? Fx is nothing but axial force, which is also equal to change in the momentum of the wind. So as the momentum of the wind changes, that will be converted into axial force, where delta m dot V, m dot is nothing but mass flow rate and V is nothing but velocity. So m is mass flow rate, so rho A into Vt, it is the continuity equation. M is equal to rho A V is the continuity equation. Substituting that value of rho A into Vt in the Fx equation, so that is rho A Vt into change in the velocity is nothing but initial velocity Vi minus final velocity Ve. So substituting all these things, so we will get the following expression, where Fx already we have derived as rho A into Vi square minus Ve square by 2, which is equal to rho A into Vt into Vi minus Ve. So here Vt, so that is nothing but you can take it as a average velocity or total velocity that is inlet velocity plus exit velocity divided by 2 is taken as Vt. Now the general energy equation between the section I and E is nothing but W is equal to kinetic energy at the I minus kinetic energy at the E. So that is equal to Vi square minus Ve square divided by 2. Okay, so the power is defined as power is equal to what? Power is nothing but force. So power is nothing but in terms of watt, force is nothing but in terms of Newton, force is equal to Newton. Okay, so power is nothing but in terms of watt we have to derive. So therefore when power is multiplied by the mass flow rate m dot, then Newton per second, okay, kg per second will be the power. Therefore power is m into Vi square minus Ve square by 2. Here m is what? Rho a into Vt, we have already discussed here. So that is mass flow rate. Substitute that one in the equation of m, then power you will get rho a into Vt, which is multiplied by Vi square minus Ve square by 2. So now this is the expression for the power. Again combine the equations of above two equations. Finally power is equal to 1 by 4 rho a into Vi minus Ve into Vi square minus Ve square. Again for maximum power, so it will exist at the optimum exit velocity, that is Ve optimum. So Ve optimum means, so we see that velocity will not be always same in the wind turbines. So velocity, it keeps on changing every moment. Therefore optimum velocity we have to consider. Therefore differentiate the above equation with respect to Ve and equate it to 0, then you will get the optimum velocity. The same thing we have done here. Dp by dve is equal to 0, where dp by dve is equal to 3 Ve square plus 2 Vi into Ve minus Vi square. So this is the derivation, the so this is the differentiation of the 4.15 equation with respect to Ve. Now apply the boundary conditions, that is V is equal to Vi. Suppose V is equal to Vi and V is equal to 1 by 3 Vi. Two types of answers we will get. So now optimum velocity, V exit velocity cannot be equal to Vi. So why it cannot be equal to Vi? So this is one solution. Even though we cannot use this solution because exit velocity cannot be equal to inlet velocity. So we will ignore this and we will consider this expression. So exit velocity should be 1 by 3 times of 1/3 of inlet velocity, that is considered. Now that will be the optimum velocity. Ve optimum is equal to 1 by 3 into Vi. So substituting this we will get the expression for the P maximum, that is maximum power. Now in the above equation 4.15, substituting this equation and simplifying, we will get P maximum is equal to 0.595 times of a P total. So this is what that is called as power coefficient, that is P maximum divided by P total. So here I will write P maximum divided by P total is equal to what? Is equal to 0.595. So theoretically we have proved that. So maximum 0.595 times of energy we can get from the wind turbines, whatever may be the total energy input, that is 59.5% of energy extraction is possible. So that's what, where 0.595 is a fraction of power which can be extracted from the wind stream, and it is known as power coefficient. Mathematically we have proved it. So this is also called as Betz limit or Betz coefficient. So the scientist whose name is Betz, he has derived that. So whatever may be the design, whatever may be the material, only 59.5% of efficiency or conversion fraction you can get the energy from the wind, not more than that. Okay, so now in continuation of that we have to derive some more derivations, that is forces on the blades and thrust on the turbine. So what are the forces exerted by the wind on the blades. So that for that we have to derive the equation. And what is the thrust, axial thrust, which makes the turbine to move or rotate. So in this section, propeller type of wind turbine is considered. There are two types of forces acting on the blade. One is the circumferential force acting in the direction of wheel rotation that provides the torque, and other is axial force acting in the direction of wind stream that provides the axial thrust. So if I write the rotor like this, so here one force is acting, that is called as that is called as axial rotational force. Okay, so that makes the turbine to rotate. And another one is, if it is the shaft, in the direction of shaft, so the axial force or axial thrust is acting. So two forces are acting. One causes the torque, so this causes the torque and makes it makes the rotor to move. And another one is axial force, so that provides an axial thrust on the bearings. Okay, now torque is what? Torque is nothing but power divided by angular velocity. Power is what? P. Angular velocity is what? Pi d into n, where pi is um, the constant value and d is the diameter. Okay, and n is the speed in terms of rps. Okay, revolutions per second. So torque is expressed in terms of newton meter. So this is not newton, this is actually newton meter. Torque will be expressed in newton meter. Angular velocity in meter per second. Okay, okay, and diameter, that is diameter of the turbine wheel, 4 by pi into a, so that is meter. N is revolutions per time, that is rps, or second to the power of -1. Substituting all these values, then we will get the real efficiency. Eta is equal to P divided by P total. So this is what we have already derived. So P is equal to efficiency into P total. So efficiency term eta into half into rho a V cube is P total, we have derived already. Now torque is what? So torque is eta into rho a V cube divided by 2 pi dn, which is equal to eta into half into pi d square by 4, which is nothing but area of the rotor, into rho a vi cube divided by pi dn. Now this is the expression for the torque. So for the operating power P, we can write. So T is again simplified as eta into 1 by T rho d vi cube by n. So here at maximum efficiency 16 by 27, or what we call 0.595, that is Betts limit, we have discussed already. For maximum efficiency is 16 by 27, we cannot exceed that. What is the expression for the T max? For maximum efficiency 16 by 7, substitute eta value 16 by 7, and what the corresponding T you get, that is called as T max, maximum torque. Maximum torque for this one will be 2 divided by 27 into rho d vi cube by n. So this is the expression, and we have to derive the axial thrust expression also, that is Fx is equal to half rho a into vi cube by minus vi square minus ve square, whereas that is pi by 8 rho d square, okay, into vi square minus ve square, because we have derived the expression of a as pi d square by 4 and substituted here. So the axial force on the turbine wheel operating at maximum efficiency, where ve is equal to 1 by 3 times of vi. So this is optimum velocity we have discussed in the previous slide. Substituting that, we will get Fx maximum as 4 by 9 rho a vi cube, or Fx maximum is equal to pi by 9 rho d square into vi square. This is the expression. So with this torque and forces expression on the wind turbine, as well as power density and power coefficient derivations, we have solved. So far we have solved power expression, maximum power, total power, power density, torque expression, axial force expression and power coefficient expression. 7 expressions we have derived in this derivation, and in the next class we will solve one problem on the wind turbine, so which includes all these expressions and the calculation methods of all these things. Okay, so with this I will conclude, and all the derivations in these subjects are over. Only one more problem is left out, so that we are going to discuss in the next class. Hope you understood, and I will share these notes also. Please go through the derivation several times until you get familiarized with the derivation. Thank you very much.